Welcome to Lecture 25 for Physics 4B. We continue our coverage of time-dependent circuits, looking at oscillating circuits. In the first half of this lecture, we analyzed the LC circuit, which exhibits oscillating behavior, sometimes called ringing, in reference to how the circuit response appears when driven with a square wave. And in order to analyze the more realistic version of this circuit, LRC circuit, we introduce complex exponentials, which will make a detailed analysis of the LRC circuit possible. Next week, we will look at AC circuits, which are driven by an oscillating input signal. So how inductors store the energy? That's the easiest to see in what we call LC circuit, inductor capacitor circuit. So this is what we call LC circuit. For the method that we are going to work out on Monday, we will be considering this circuit, capacitor just hooked up to inductor. Now, this obviously won't do anything interesting just by itself, right? So I have to charge it up. I have to get it started somehow. Charge up this capacitor to start out with. So that is plus Q naught and minus Q naught. And at time equals 0, everything is connected and starts to flow. And actually, here's the way you can imagine it. It's the same thing that we did before, except I rotated it around a little bit. So you can imagine that, all right, there's going to be a battery here. And when I have this battery of voltage V naught, call this point A, point B. And another switch here again. I imagine connecting this switch to A. This battery applies a voltage difference. So the charging, it's going to look a little bit complicated because of this inductor. But one thing I can say is when I'm done charging, so that there's no more current flowing through this whole thing, then the voltage drop across this two will be 0. Current is at 0 and not changing. So once this is all charged up, then I'm going to, with 0 current, I'm going to flip this over to B, and I'll tell you what happens. The circuit oscillates. The charge here, it'll start to flow. Because of this charge separation, there's a voltage difference. That voltage difference is going to drive current through the circuit. More precisely, it actually drives a rate of change of current through the inductor. Because this voltage difference is this voltage difference. So current increases from 0. Now, around the time when this discharges completely, when the charge only goes to 0, what you're going to have is you're going to have maximum current on the inductor. And it won't stop there. Because, well, if you have current here, it'll continue to flow, right? Which means at some point later, the charge on the capacitor will be reversed. You will have positive Q here and minus Q here. So that'll start creating voltage that'll oppose the flow of current. So that'll start decreasing the current. And at some point, you're going to reach maximum charge here and 0 current. Then there's still voltage difference. So there'll be current being pushed back again. And then this will repeat over and over, ideally forever. You can look at it as energy stored on the capacitor, going to energy stored in the inductor, back to energy stored on capacitor, back to inductor, and so on. In real world, the reason it would stop is for the same reason any motion stops, because of resistance, because of friction. So here I can create a small circuit version of that kind of illustrates it. So this is the way I will have it hooked up. So I have my inductor here. And the value of the capacitor, I was just playing with it before class. And the one that I found that works is this is a 0.01 microfarad capacitor. It's a pretty small capacitor. I'm going to put this in series with my inductor. And I'm going to drive a square wave across this thing. And I want to be measuring voltage across the capacitor because that'll give me the amount of charge on the capacitor directly. Better than anything. So once again, ignore what you see on the driving thing. I think this will be actually more interesting, yeah. So I need to set up the time scale. so that I don't need to be on such a high frequency anymore. I think this is not good enough. All right. Okay. Let me trigger on the falling slope. So when you look at this curve, let me just explain what it is so that you can relate it to what I was just describing. So this is the voltage of the power supply. That's the moment before I triggered it, it was on. So it was on at this value. So the battery was charging the capacitor inductor circuit, and then it suddenly dropped to 0, connecting it, into the form that I put there. And what you see oscillating here, that's the voltage across the capacitor. That's the amount of charge on the capacitor. And you see that it oscillates. Let me zoom in the time a little bit. All right. So you do start out with the maximum amount of charge on the capacitor. It discharges, but when it reaches 0, it doesn't stop because the current continues to flow through the resistor. It gets negatively charged, and then when it's maximally charged, then the current flows back through the inductor again, and then when it completely discharges, it doesn't stop, keeps on going. And what does this remind you of? Motion of a mass on a spring, right? Like if you had mass on a spring, and you charge up this system, you pull it down a little bit, and when you let go, when the potential energy goes to 0, it doesn't stop because the energy went to kinetic energy. That makes it keep on pushing through. So it goes through another potential energy maximum, comes back. And there's actually a perfect analogy you can draw between this kind of LC circuit and this mechanical system. And I guess I'll just leave it there. So on Monday, we will actually go through the math for this circuit and show that it does show oscillating behavior that you already saw. So when you're trying to analyze a circuit that you haven't seen before, where do you start? Like, what's the general purpose tool that you have that will let you analyze any circuit that you see for the first time? Yeah, Kirchhoff's rules. So there's the loop rule and junction rule. And with the DC circuit, we use both set of rules because DC circuit is simple, so we can make the circuit more complicated. As we're dealing with this time-dependent circuit, because there's only finite amount of time in the world, in class and during the exam, so I'm going to give you a simpler circuit. So most of the time you won't have to use the junction rule because it's such a simple circuit that you have only one loop and no junctions. But you should use the loop rule. So imagine this is my loop. So this is going to give me my loop rule equation. And using the Kirchhoff's loop rule, we can say that sum of all the voltage changes across the loop or around the loop is equal to 0. So let's apply this. This will continue to hold true for all the circuits that we are analyzing. So let's write out all the changes of voltage as we go around this loop. So I specified my initial charge this way. So I will define my sense of direction in a way it's consistent with this. So as I go across the capacitor, do I gain or lose voltage? Gain voltage, right? I'm going from negative to positive plate. So, and amount I gain is here. So as I go across the capacitor, I'll gain plus, and I'm going to write charge as a function of time. So, at time equals 0, it's Q naught, but so I want to use this equation to set up a differential equation that I'm going to solve like I solved it for RC and LR circuit. So it's going to be plus charge as a function of time divided by C, the capacitance. It has to be given to you somehow. And all right, so that's the first element. This is close to its wire. As I go across the inductor, do I gain or lose voltage? You better lose voltage so that you come back to 0, right? So let me write this out this way. Minus L di dt. So that's the voltage change across the inductor. And I put this minus sign here so that it's a reminder to me that I'm supposed to be losing voltage as I go across this inductor of inductance L. Okay. So all of that done, it should add up to 0. That's a Kirchhoff's loop rule. All right, so I have one equation here. Now, do I have enough information to actually solve this? How many unknowns do I have? I have 2. I don't know the charge as a function of time. That's what I'm trying to find. That's what I'm interested in. I know the charge at time equals 0, but I want to know what the charge is at some later point in time. And I also don't know the current as a function of time. So there's 2 unknowns, which means I need at least one more expression. And where do I get that? Yeah, current through the capacitor. That's given as the rate of change of the amount of charge on the capacitor. Because whatever current comes out is the charge that's on here that's flowing out, or whatever current goes in will accumulate as charge on the capacitor. Right? Now, this is the step, as we did last time, on last Wednesday, where we have to be careful with the sign. And really, this is all this comes down to. All these choices that I've made along the process here, all these positive signs I've written down, this minus sign I've written down, all those come down to a choice of a positive direction that I've made those choices. And all I have to do is make sure that however I choose my sign here, plus or minus, that this choice is consistent with these choices that have already been made. So actually here, I made it sound like this has to be positive, this has to be negative. They don't have to be. It could have been negative and positive. The loop that you have to close is where you choose the correct sign here. So by the choices you have made here, you are constrained into whatever sign that you pick here. So this is where I have to imagine this. So this is the initial condition I've set up. As this charge flows out, I'm going to say this is my positive direction of current. So my current is increasing, right? Increasing from 0 to some positive value. So my di dt is positive, and all of them make sense. That's why I needed a minus sign here so that the voltage would drop across the inductor. Now, for that picture there, where charge flows out and positive current flows, do I need a plus sign here or a minus sign here? What is the sign of my dq dt? dq dt is negative. It's decreasing. Current, I want that to be positive. So here, I need to pick the negative sign so that minus times minus works out to be positive. So this is the exercise that you have to go through every single time. At least I do that every single time. You could memorize a set of rules that would just have you picking the correct sign each time, but I think this is simpler. To take a snapshot that you are given, the initial condition, and make sure the choice of sign you make here is consistent with everything that you have done so far. Question?
How do we know that the rate of change is negative?
So I'm looking at around the time equals 0. That makes it easier to visualize this. I know at time equals 0, I start out with the capacitor charged. And intuitively, I know this starts to discharge, meaning the amount of charge decreases. So when amount of charge decreases, the rate of change is negative. Yeah. Yeah. All right. Okay, so I have 2 equations, 2 unknowns. So, I mean, this is not algebra, but intuitively, I probably should be able to solve this. So let me actually plug this in here and do the same thing that we were doing before. Before, what we were doing was, we had this equation, we brought in the second equation, and we plugged it in the expression for current, and got some differential equation that we solved. Right? That's what we did for RC and LR circuits. So let's do that. Plugging in I into here, this is the equation I end up with. Q as a function of time. So I'm going to get a single equation in terms of a single unknown, Q. of t over c, minus times minus, so plus L times one time derivative, and on top of that, another time derivative acting on it. So second time derivative of q as a function of time is equal to 0. All right, let's do the same thing that we are doing with differential equations so far. With the differential equations, what we have been doing was we take the highest order derivative we see and we solve for it. That gives us some kind of standard form that we can use as a starting point when we are trying to use our solution techniques. So solve this for my second order derivative, then I get this. Second derivative of q is equal to, move this over, so minus q of t, and divide out L. So minus 1 over LC times q of t. How many here have solved second order differential equations before? How many here, is it math 3E or 3F? I keep switching those numbers around. 3F is the differential equations. How many here have taken math 3F? Some of you. So actually, if in 3B and 3C, you will not have seen a solution to this yet. Can you use separation of variables to solve this? Not really. Like, how would you separate? Like, you know, if you, I mean, as a physicist, I'm usually okay with abusing notations. But even with that physicist standard, if I write down something like this, it's kind of a nonsense. You know, this is what we would do if we are trying to do separation of variables. I have no idea what this dt squared means. I have no idea what this d squared q means. So, you know, as a physicist, I'm okay with abusing some notation, but there's a limit, and this is my limit. Because differentials make a sense when it's just a sort of single order differential. When it was dq dt, I could do that. I could imagine that dq dt was really delta q over delta t and separate it out that way. But when it's a second order differential, doing that really, because, you know, with the second order derivative, really what it's trying to say is this, and it gets more complicated. And what I'll tell you is that there is a solution technique that you will learn in math 3E, or 3F, whatever class is the differential equations. And that is beyond the level of math required for this class. So how are we going to solve this? I mean, this class does cover LC circuits. It is one of the standard topics. I mean, I do spend more time on circuits than many other physics instructors do because I love circuits. But it is a set of standard topics. It's not something exotic that I'm bringing in from upper division level. It's something that we should be able to do. So given that we don't have the tools, how are we going to do it? Yeah, you said guess, right? Yeah, we are going to guess. Nothing stops us from guessing a solution. And so we don't have proper formal mathematical tools to actually, you know, in a systematic way, get a solution to this, but we don't need it. We can simply guess a solution and check it. So in fact, we actually did that in physics 4A. When we did oscillations, we actually got an equation of motion that looked awfully similar to this. And we got a solution to it, and you knew even less math back then. So we are going to use the exact same approach. This is the thing about differential equations. If you are trying to go from the equation to get a solution, that's usually a difficult step. It comes down to integration is more difficult than derivative. But once you have a solution, it's really easy to check because all you have to do is take the derivatives. So I guess the only thing that you are missing out on when you do it that way is in math class, I guess they spend a lot of time on like a uniqueness of solution or like have you found all the solutions, that sort of stuff, right? So we're gonna miss out on that, but we have some sort of intuition that, you know, it's second order. If we find the two solutions, then we think that's gonna cover everything. So. So we're going to guess a solution to this. So this is where having some mathematical intuition is helpful because, we can just start guessing randomly. Is my Q of t equal to t? Or, is it proportional t? Or is it, t squared? Or is it t to the third? Like we can just start guessing random functions, but that's not going to be very efficient, right? We have to make educated guess. So as you look at this differential equation, you should have some sense of, if you're referring back to physics 4a, that's fine. But for those of you who don't remember what we covered in oscillations, you have to sort of look at some properties of the function q that's evident from this differential equation that this function must satisfy. So what are some properties of the function q as a function of time that's going to satisfy this equation? Anything you see in this equation where this must be true about this function q of t?
Can't be 0?
Well, actually it can be 0 because the double time derivative of 0 is 0, and 0 is equal to minus 1 over LC times 0. That's what's called the trivial solution in math. So we know that's a solution, so we're going to just stay away from that. It's a solution, but it's an uninteresting solution. Okay, so let's think of a function that's not 0 and still an answer to this. Can it be a constant function? No, right? If it's constant non-zero function, then this is not 0, but your left-hand side becomes 0. So that doesn't work. Can it be like a linear function? Like q of t is proportional to t. Why not?
Because when you take the derivative of the linear function, for example, with ax plus b, you get like a.
Yeah, you get constant. And
Second derivative is 0.
yeah, so you take another derivative, so you get 0, and that's not equal to whatever function you started out with. In fact, here's something that we are seeing constrains us. As we take two derivatives twice, somehow we come back to the same function. So can this function be a polynomial function if this is true? Q of t, can it be any finite polynomial function? Like if it's a fourth order polynomial. It doesn't work, right? Right-hand side is a fourth order polynomial, but after you take two derivatives, you're going to get second order polynomial, which cannot be equal to fourth order polynomial. So this is the most distinguishing feature of this function q of t, that after you have taken two derivatives, somehow the function that you get back is going to be proportional to q of t. So let me write it down this way. Q double prime is proportional to q. When you have taken two derivatives, that it's proportional to the original function before you took any derivative. Any functions that you know that satisfies this property? You must have seen some functions that's not polynomial function, so it must be some kind of special function that actually satisfies this. That when you take, as you take derivatives, the function doesn't change much. Yes, Chris?
The exponential function?
Yeah, exponential is one of them. So this could be satisfied by something that looks like exponential of t. Now, as you consider this, so one of the things that might motivate this case is that you have been seeing exponentials so far in the circuit, but you run into a little bit of difficulty that you didn't have last time. So let me actually write down a proper form that has all the necessary constant in it. So q of t, so it's going to have general form of exponential of t. And it needs a couple constants to make the units come out right. So let me write in those two constants that have to be there to come out to make the units come out right. The exponential function itself gives a unitless quantity, so you need a constant here so that you have unit of charge. Exponential takes as input unitless number, so you must have another constant here that's going to be canceling out unit of time so that you have a unitless number here. Now, imagine, or do plug this into here. So you are going to take 2 time derivatives. When you take 2 time derivatives, this is what you end up with. Q double prime is equal to, each time derivative leaves the outside the function alone because it's exponential. And you use the chain rule, take the derivative of the inside, you get a factor of b out. So you get, so first derivative takes out one factor of b, second derivative takes out another factor of b, so you get b squared times a exponential of bt. And you recognize this as your original function, that's what you're going for. Say that this q double prime is equal to b squared times q. And you compare this result to the differential equation that you're trying to solve for, really guess on solution to. And do you see anything that's potentially problematic here? So let me finish the last step, plug this in here. So what we are trying to say is that b squared q is equal to minus 1 over LC times Q. And Q cancels out. So it looks like we are imposing some kind of condition on this parameter B. And the condition is that B squared is equal to minus 1 over LC. Is that a condition that can be satisfied? How do you satisfy this condition? What value should B be? I mean, if I write down B is equal to square root of minus 1 over LC, anybody got any issues with that?
Are we using imaginary numbers? Or?
So if we are using imaginary numbers, yes, we'll have an answer for B. But in fact, that's what we are going to spend most of our time today. So this is, by the way, something I am doing that actually is not in the standard curriculum. I tried this last semester, it worked out pretty okay. I'm going to introduce complex exponentials in this class because a lot of this math that we do with AC circuits becomes a lot simpler once you know how to work with the complex exponentials. So yes, if we allow B to be complex, as in allow it to be imaginary, then sure, we can do that. But right now, let's stick to real number so that we can at least get an answer here that's within our mathematical toolbox. So this is really going to be a limiting factor. That it's right for the time being. It's not going to be in a little bit. But for the time being, if you are insisting that our B is in the set of real numbers, then this is not possible. Because L is positive, C is positive, so this is negative number, square root of negative number, that doesn't exist within real numbers. So this doesn't work. And that's really why this guess, for the time being, doesn't work. We're going to revisit this, and complex exponential will actually become one of the best guesses for many different circuits in a little bit. But for now, because we are limiting ourselves to B being within the real set of real numbers, all this line of reasoning gets stopped by the fact that this coefficient here is negative. So let's actually write it down as one more property of Q of t that we have to take into account. The property of Q of t is that when you take the double derivative, it's not that it's just proportional to Q. It's actually proportional to minus Q. And this minus sign actually matters because it limits what forms of solution you can take. So let's go back to generating guesses again. What functions do you know where after you take the double derivative? So we are not really looking for a function that doesn't change like exponential. We are looking for a function that does change, but changes in a way that there's this minus sign that gets introduced. I mean, you don't know that many special functions. You guess the exponential. What other special functions do you know? You know logarithm. Now, logarithm, does it feel like logarithm would work here? No, single derivative will give you 1 over q, and then the next derivative will, oh, you get a minus sign. Minus 1 over q squared, but okay, that's not logarithm, so that doesn't work. Okay, you've guessed the exponential logarithm. What other special functions do you know? Like you're literally down to your last 3, or depending on how you count, last 6 special functions. Unless anybody here have heard of hyperbolic functions? Yeah, normally you learn about hyperbolic functions after you learn about complex exponentials, so that wouldn't be in your toolbox. Really? Everyone here knows only exponential and logarithm? You could not have taken calculus without knowing a few more special functions. Yeah, trigonometric functions. That's the last class of transcendental or non-polynomial functions. So I guess maybe what you're thinking was, if you have sine and cosine, when you take the derivative, they change. That's maybe why your thought was going that way. But what you have to, so this might have been escaping your notice, and this is actually important part. We are not taking first order derivative. We are taking second order derivative. We are taking 2 derivatives. That's going to matter. So we can have 2 different guesses. We could say our q as a function of time is equal to proportional to cosine. So we could say it's cosine of, let me just put in all the proper coefficients now. So we do say it's some coefficient a times cosine of, and I kind of remember the coefficient I was using here before, angular frequency. So let me just use omega here so that I limit the number of symbols I introduce. That's one form of a solution I could have. And since cosine and sine are kind of in the same category, let's try them out both together at the same time. Second form of the solution would take the form of sine. And I need a different set of coefficients to, so this one will be b times the sine of, and I'm just gonna go with the gut feeling that it'll be the same omega. So I'll just use the same symbol omega here. So let's try plugging these in and see if there are solutions. And you will see that when you take a double derivative, that's where these will actually work out. So let's do that here. So let's take the first guess. To plug this in, we need the first derivative of q of t. So first derivative of our first guess is going to be a times derivative of cosine is minus sine. Minus sine, so derivative to the inside, so a factor of omega comes out. So it becomes minus omega a sine of omega t. And this is what most of you are thinking when you weren't suggesting that trigonometric function might work. Let's take another derivative. My differential equation deals with a double derivative. So taking another derivative of sine is cosine. And derivative to the inside, another factor of omega comes out. So I get minus omega squared a cosine of omega t is the double time derivative of q of t. And this is where things look hopeful, because this was my q1 of t. So compare this with my differential equation here. You get this answer. So this is a solution if and only if that omega has a correct value. If and only if omega is equal to, or omega squared is equal to 1 over LC. Or omega is equal to square root of 1 over LC. Is this beginning to remind you of the oscillation topic that we covered at the end of Physics 4a? We did this like in week 12 or 13 of Physics 4a, or maybe week 14, I forget. Right? So yeah, if this is reminding you of it, it should. Because when we did this demo, you saw something oscillate. So it should make intuitive physical sense that we are getting oscillating answer here. And we might even say this is the natural oscillation frequency of LC circuit. Because with this demo, what you saw was that I had a kind of a strike or a sudden shift in the circuit, and nothing was actually trying to drive the circuit at this frequency. But when you actually measure this period and try to calculate that frequency of oscillation that you saw, you'll find that that's predicted by this formula here. Good. So, okay, let's wrap up this discussion. So we found a solution. Since we had the second guess, let's finish it up and see if we have more than one solution. So, take this, plug it in here. So we have to go through the exact same steps. So I have two solutions. What should I do? Which of them is correct? They can both be correct. So this is a concept that you would cover in your math class. I guess they call it general solution versus either specific or specific solution. So when you have a differential equation like this, there's a general solution. General solution is the solution that contains these kind of parameters that are analogous to integration constants. As in, these are undetermined by the equation itself. Omega is determined by the equation itself, but with each of these solutions, we get these parameters that's not determined by equation. What determines these is what we call initial conditions. So let me use the language that you will see in your math 3F class. So the solution to these are the general solutions. The most general form of an expression Q of t that would satisfy this equation is this. It's essentially a sum of both of these. This is something that's covered under something called a linearity. If one is a solution to a linear ordinary differential equation and the other one is also, then their sum is also a solution. So general solution here is Q of t is equal to this thing, a cosine of omega t plus this thing. That's why I used a different letter here so that I can add them later without implying anything. Plus b sine of omega t. And I'll leave it to your own exercise that if you plug this into the differential equation, it is indeed a solution. So that's the general solution. Now, for this specific question that we are asking here, we have to put in initial conditions to get the specific solution. So what I'm saying here is to obtain the, I may be using the wrong term. I always get this term wrong. I'm saying specific solution. Mathematicians might use something different. To obtain, I'll just say specific solution. Or is it particular? Who here has taken, is it particular solution? Okay, to obtain a particular solution. Particular solution. You have to put in the information that was given in your problem. It said that charge is equal to this at time equals 0. It said, so we need to plug in initial condition. In our problem, that would be charge at time equals 0 is the amount of charge that was initially on the capacitor. So when we plug in this set of information, this is what we end up with. That so at time equals 0, so let me write down what Q of time equals 0 is. A times cosine of omega times 0. What's the cosine of 0? 1, all right? So A plus B times sine of, what's sine of 0? 0, so B times 0. So, all right, so this condition does give me that A is equal to my initial charge Q naught. But do I know what the B is? Yeah, I don't. So actually, this initial condition that we figured out, or that was given, it fixes one of the two parameters that I get from my two independent solutions. So I actually need two initial conditions or two boundary conditions to actually fix my solution completely. Any ideas where else we might get that? So, yeah.
Did you charge at t equals infinity?
Well, it's going to oscillate. So here, it's oscillating down to 0, but that's only because there's some resistance there. If it's an ideal case, it'll oscillate forever. So at t equals infinity, the charge is undefined. This is a general feature, but since none of you have, or many of you haven't taken differential equation yet, I'll just give it to you, and you will see it in your math class. For the second order differential equation, the way to specify a complete set of initial condition is the initial condition for your the parameter and initial condition for the derivative of that parameter. So what's the derivative of Q? That's the current here, right? So if we know the current at initial time, that will give us the complete set of initial conditions. And yes, so we do know the current at time equals 0. So plug that in. So current I, or that would be minus dq dt. Well, that's equal to, let's just take the derivative of this in our head. That's minus omega A sine of omega t plus omega b cosine of omega t. We are evaluating all of this at time equals 0. So sine of 0 is 0. So A actually, this term actually goes away. So this gives you the saying that all of this is equal to 0 at time equals 0. That gives you no information about A, but that's fine. I knew that already. And the second information is here. So at time equals 0, cosine of omega t is 1. So I guess B is equal to 0. It's going through a lot of steps to figure out that B is equal to 0, which many of you might have guessed already. So this is the solution step that we go through to solve this second order differential equation. So what we are essentially doing here is we are turning this problem into differentiation and algebra problem by saying that, okay, we give up, we don't know a systematic way to solve for it. We are simply going to guess and check. We do make an educated guess, and once you have found the general solution by guessing, then finding the particular solution is an exercise in algebra. Just plug in the snapshots that are given to you. That gives you, all right, A is equal to that, and B is equal to that. So for this particular case, this is our particular solution. Q, as a function of time, is equal to, A is equal to Q naught, and that was cosine omega t. And this is the solution to this differential equation, which you might remember as if you are trying to look up what should covered in physics 4a, this was actually called equation of motion. And what we are working with right now is the circuit analogy of equation of motion. So that satisfies this equation of motion, while at the same time satisfying these initial conditions. Q of t equals 0 is Q naught, and current is 0 at time equals 0. Okay. So that's it. This is the LRC circuit. This is the full solution. And what I'll tell you is that this whole thing about guessing the answer, if you stop with the guess, you are not doing it properly. You have to check your guess. And in fact, in the process of checking your guess is where you get this little nugget of information that you didn't know before, that the natural oscillation frequency is given by your component values. You will see this in your lab. Okay. I think I want to call this complex exponentials overview. So this is a topic that I really want to give a treatment as a part of a lecture, because it's the kind of thing that does get covered in math classes leading up to here. But both of these ideas, complex numbers and the idea of complex exponentials, I find that they don't get enough proper emphasis in a math class. It's the kind of thing that we can really only properly cover with the right kind of emphasis and with the real applications you see in the real world. That kind of coverage is really only possible in a physics class or an engineering class. So I want you to give this overview. Let me point out some things so that I think it's good for everyone to be aware of. So this comes out of a question maybe about a year ago. One of the students in my physics 4B was asking for a written material covering this. I think he didn't want to watch it through, or he watched it through the lecture videos. And as I say often, it's beneficial for you to see different treatments. If my lecture doesn't fully make sense, then I do want you to have written materials. And this is the sort of thing that lower division physics textbooks don't cover all that fully, and I think a lot of upper division textbooks assume that you are familiar with it, and it was a bit of a struggle to find the right written content. The one resource that I found that should be accessible at your level while covering the sophisticated ideas is Feynman lectures. So let me just show it to you here. So Feynman lectures, it's available on Caltech website. It didn't used to be this way, but you can read it for free. And I think the content I'm looking for is both in volume 1 and volume 2. So within volume 1, it's covered under algebra. Very deceptive title. But I think this board picture tells you what he'll be covering. It's a coverage of the mathematical ideas that I think you're already familiar with, but the level and depth of conceptual coverage that you can get now, now that you've taken calculus, you have a degree of mathematical maturity. This is a good overview for you to see with a more mature view towards algebraic operations that you've learned, what kind of significance is there, and how to generalize known operation into so far unknown domains. Yeah. So what I hope to do in the next 10 minutes or so is not a replication of what you see in Feynman lecture. For that, I will leave that up for you to read the Feynman lecture. What I want to give you here is a practical application and overview. So we should start out with an overview of complex numbers. You learn about complex numbers first in an algebra class because the place where they come from is in attempt to solve algebraic equations, polynomial equations like this. X squared plus 1 is equal to 0. And when you go through the manipulation of symbols and try to solve, what you end up with is this expression, x is equal to square root of minus 1. And this is the kind of number that if you're thinking of real numbers only, numbers that you think of by starting from counting 1, 2, 3, and thinking of fractions and thinking of things that can be approximated with decimal representation. Here, what you're looking for is a number such that when you square it, you get a minus 1. And that's not a number that fits within our paradigm. So when mathematicians faced this question, they had to come up with a new kind of number. So the new kind of number that they came up with was given a symbol I, standing for imaginary number. And I think sometimes people get misled by this adjective of imaginary number. As in imaginary numbers are not real. But it's there are very real uses of the imaginary number in physics and engineering, and that's what I hope to show here. Let me remind you of a couple of things that you have seen as you are being introduced to complex numbers. So you will have seen this representation of complex number. So a complex number G can be expressed as a real part added to an imaginary number times the imaginary part. This would be one very natural way to express complex number. I think from my perspective, it's more natural to introduce the complex plane next. Because here's the interesting thing about complex numbers. So we are used to numbers having a one degree of freedom, as in you pick a number, and that choice of a number completely determines the number. But when you look at a complex number like z, it has 2 degrees of freedom. You can specify the real part independently of the imaginary part. So these have 2 degrees of freedom. And if you are thinking of other mathematical objects that have 2 degrees of freedom, I hope it doesn't take you too long to think of vectors, vectors in two-dimensional space. And in fact, that's what complex plane represents. So when you represent a complex number on a complex plane, you have 2 axes that span the plane, and one of the axes you associate it with a real component, the other axis you associate with the imaginary component, and any point in this plane can be characterized with the real part and the imaginary part. And so this point here, if you are using this complex number, the real part would be A and the imaginary part would be B. And so we can choose to represent this complex number by these coordinates, A and B, in the complex plane. And once we start drawing this comparison to geometric representation of vectors, then you can see other ways of representing this mathematical object. So if you're thinking of this like a vector, so what we have here could be described as the Cartesian representation. It's describing the magnitude and direction of the vector by specifying their x and y coordinates. That's one way to do it. That's how we very often dealt with the vectors. Now, if what you're interested in is magnitude and direction, then you could specify that magnitude and direction just directly, the way you would do in the polar representation of vectors. And I guess if you are thinking in terms of analogy between two-dimensional vectors and complex numbers, we can go as far as this. We can say, oh, this theta, it looks a lot like the angle that we define this way. Tangent of theta is the rise over the run, or opposite over adjacent, or A over B. And the magnitude R, looking at the geometry, we could say R is equal to square root of A squared plus B squared. And remember, A and B are both real numbers because I have this I separated out here. And you could describe the polar representation this way. And there's nothing wrong with it. At the same time, I guess it might feel like we didn't really gain much. We just turned on algebra problem, which would describe this solution to polynomials and this way of describing complex numbers. We just introduced some geometric idea, And we don't really get any payoff. We don't get any simplification of any calculations we might have done, because these formulas are kind of complicated looking formula. So if you're just stopping here, it's hard to see what we gain from this. And this is where what you learn in pre-calculus comes in very useful, which is what's described as Euler's equation. And Euler's equation says that exponential of an imaginary number, I times some parameter x, can be written out this way. Cosine of x, which you know how to calculate, just real valued function, plus I times sine of x, another real valued function. This quantity on the left-hand side is something that if you are seeing it for the first time, you might wonder what it means. We know what exponential of real valued parameter is like. But here, you are not looking at a real valued function of exponential. You are looking at a imaginary valued parameter going into exponential. And really the way to make a sense of that, it's the tool for that is given in your last semester of calculus 2 or math 3b. You are introduced to Taylor expansion polynomials, and that's how you can make a sense of this formula here. Let me demonstrate briefly using Sage Math. Okay, let me show you some Taylor polynomials. Let's say I'm going to define a function f as cosine of x. Okay, and I think there's a Taylor series. Yeah, okay. Itself x 0 to the 8th degree for cosine. There it is. Okay, I want you to read this kind of backward. So I have 1 minus 1/2 x squared plus 1/24 x to the 4th power and so on. This is the Taylor approximation of cosine. Let me define a new function, g, as sine of x, and take the Taylor expansion of it to the 7th degree. I think that will give me the same number of terms as before with the cosine. So I have x minus 1/6 x to the 3rd power plus 1/120 x to the 5th power minus 1/5040 x to the 7th power and so on. Now, let me get a new function, h as an exponential of g, and let me take the Taylor expansion of this function of g about 0, and let me do it to 8th order. And when I do that, I hope this is what you can see. There's a kind of a similarity that you can match up these terms. 1 to 1, the 1/2 g squared to minus 1/2 x squared, and so on. You can, for each one of the terms that you see here, 0th through 8th order term, you can match them up to either cosine or sine's Taylor expansion. And this Taylor expansion is how you can draw an equality between these two terms. So if I make this a substitution, I'm going to take this expression and substitute g as imaginary number times x. And equals. And let me see what it does. I think I want to kind of full simplify it, because I think if I do full simplify, it'll kind of factor things out. Well, it didn't. but okay, you can make this a useful comparison. Look at all the terms that don't have imaginary number I. That's because they come in even powers of g. So when you take even power of imaginary number I, then you can either get plus or minus 1, but you won't have I. All those terms, all those real terms, they match up to terms in cosine of x. all the terms that have an imaginary number, because they have odd power of x or odd power of g, they match up to these terms in the expansion of sine of x. So this Taylor expansion is what justifies this formula, that exponential of ix is equal to cosine of x plus I sine of x. Once we introduce this, it gives you a wonderful simplification of some of the mathematical operations that you might do with complex numbers. Let me give you some examples. Let's imagine a scenario where we know the complex number, its magnitude and the angle theta, and we want to express the x and the y component of that, or the real and the imaginary component of that complex number. Then what we would say is that the real component, drawing on this geometry, should look like r times cosine of theta, and the imaginary component should look like r times sine of theta. Seems simple enough. And leaning on this expression for complex numbers, we can express this complex number in this form: r times, and this cosine and sine term, instead of writing them out separately, we can write them out this way: exponential of I theta. Notice how when you look at this expression for complex number in terms of the magnitude and direction, you still need 2 degrees of freedom. You need the magnitude and direction. And it has the same number of degree of freedom as the original Cartesian representation. But this particular form has a number of benefits. So as an example, imagine you wanted to calculate the magnitude r, a squared plus b squared. You can do r as, okay, I need to take the real component of g, square it, plus imaginary component of g squared, square root it. That's certainly one way to do it, but it's a very cumbersome way to do it, because it's basically doing all the geometry calculations. And it would be nice if there's a clean, quick, algebraic way to treat it. And this is where I would introduce the idea of complex conjugate. Complex number, notated with an asterisk, is another complex number that you get from a complex number. So this would be obtained by taking a complex number g, and you replace all instances of I with minus I. Or if you have any complex variables within your expression, each complex variable would acquire this asterisk. So in an expression like this, both a and b are real. So g is equal to a plus ib. This complex conjugate is a minus ib, a and b both being real quantities. You might ask, why are we defining this? What use is this? The use, it turns out, is to write some mathematical operations in a very compact way. So let me just do this calculation. No one can stop me from just doing this a little bit of algebra, of taking the complex number and multiplying it with its complex conjugate. I can just do it for fun. That's equal to a plus ib times a minus ib. Okay, let me just do the expansion. A times a squared, a times minus ib, minus iab, ib times a plus I. The order doesn't matter, so it's ab, and plus ib times minus ib, so it's minus I squared b squared. Now, so let me just write that in first, minus I squared b squared. Now, this I squared is equal to -1. So I can cancel this minus with this to get plus b squared. So you get, when you do this calculation, a squared plus b squared, we're looking at this expression here, should be equal to r squared. So here, notice how I'm obtaining the magnitude r without needing to explicitly separate out real and imaginary part. So this multiplication of a complex number with its conjugate is giving me a quantity that doesn't depend on the angle theta and depends only on the magnitude r. And here's the amazing thing. Let me do this calculation using the polar representation. Because, if this is just some funny way to do it that happens to work in Cartesian representation, great, that's interesting. But again, what use is it? Well, the use this is this complex conjugation operation. It's a representation independent. The results that are true, such as this product is equal to r squared, that'll turn out to be the case whether you carry out the calculation in the Cartesian representation or if you carry out the calculation in the polar representation. So let me do this calculation again in the polar representation. G times G complex conjugate. That's equal to the complex number itself, r times e to the I theta. And I take the complex conjugate, which would be r, it's still real number, times exponential of. Theta is also real, so nothing happens to it. I just replace this I with a minus I. Now, if you recall the exponential algebra, when you have e to the I theta, call this x if you want, times e to the minus I theta, or minus x if you want, e to the x times e to the minus x. That's like e to the x divided by e to the x. So they will cancel out. This will cancel out with that. And it results in r squared. In some sense, this is a much simpler calculation than what you saw here. And the result is the same. And when you look at this and notice the property of exponential, where whenever you do complex conjugate, then this exponential of x turns into exponential of minus x. You can see that in this representation, this represents the magnitude. Just straight away, right away, without needing to do any complicated operations. And this indicates only the direction, or I guess the direction is a bit misleading, or it's not quite what the complex parameter means. It's more properly described not as a direction, but as a phase angle. And phase as a concept is something that takes a bit of a time to fully understand. And I think what I can say at this point is that the kind of the situations where you will need to deal with a phase is when you're dealing with oscillatory phenomena. And this is why complex exponentials become so useful when we are dealing with either oscillating LC circuit or oscillating RLC circuit or the driven AC circuit. In those scenarios, the representation of the phase angle is so naturally built into this complex number representation. And you can also, express that phase using what's called a phasor diagram. When you look in your textbook in the section talking about resistance and reactance and impedance and kind of the relative phase of applied voltage and current, you see a two-dimensional diagram, two-dimensional plane that's drawn, and different vectors that are drawn on this on the phasor diagram. And there is a one-to-one relationship between what you see as a phasor diagram in the textbook and representation of complex quantities, such as complex impedances on complex plane. And really, the biggest advantage of working with the complex exponentials specifically is when you are working with the phasors, you have these quantities that naturally, by its nature, has 2 degrees of freedom. That's something that you are necessarily going to have when you are dealing with the quantities that can vary in length and that can vary in phase relationship to other oscillating quantities that you have. You are going to need to specify those with the 2 degrees of freedom. And when you use a phasor diagram, essentially what you are doing is you are using geometric reasoning. And in some sense, that geometric reasoning is intuitive. You can visualize it more easily, but it quickly runs into difficulties for the same reason I think a lot of people do better with algebra than geometry, because geometry sometimes is kind of difficult to follow in a sequential way. With algebra, the manipulation of symbols is sometimes easier than kind of a visual reasoning that you have to do with the geometry. So when you're dealing with a simple circuit like a series RLC circuit, the phasor diagram, simple geometric reasoning, works very well. The advantage of the complex exponentials and the algebraic approach becomes more obvious as you start to deal with the more complicated circuits, because once you train your skill at working through complicated algebraic expressions, those are kind of easy to work through. You just follow the rules of algebra. And so with the complex exponentials, what we are doing is we are taking what is essentially a geometry problem and turning it into an algebra problem that really makes it easier to systematically approach things. That's one. And two, which you can see more, you can appreciate it a little bit better as you work with the differential equations that describe the circuit, the equation of motion for circuit. The calculus portion becomes much easier when you are working with the complex exponentials. And it really comes from the special property of exponential functions. So, when you are taking derivative of most any function, well, you can't really, it's a different function. You have some formulas that'll tell you how to get the different function, but you're going to have to find the different function. Now, when you're taking derivative of an exponential, it becomes exponentially easier. Sorry for the pun. When you're taking derivative of an exponential, then you get the exact same function back. Well, there's sometimes a chain rule you have to apply to get some quantities out in front. But when you are expressing your dynamical quantities like a voltage, as in terms of a complex exponential, the kind of calculus that you would normally have to do becomes much simpler. When you are working with the real valued functions, this would have been in terms of a cosine or sine function, where each derivative change what type of function is and potentially introduces minus sign. When you're dealing with the exponential, you don't have, at least in the formalism, you don't have to worry about that. When you take the derivative of this with respect to t, then this outside the function doesn't change. You simply get v naught exponential of I omega t back. You have to remember to apply the chain rule to get this factor out. And the kind of the derivative you have to take is much simpler when you're dealing with the exponentials. So as you're dealing with the equation of motion, you will also see that calculus becomes easier. This kind of a calculus problem, complex exponentials will turn that into an algebra problem. And you see that simplification when you're watching the lectures, how we cover both the time-dependent and AC circuits using complex impedances. So this is an overview of the complex exponentials. Hope it's helpful. Hope this reminds you of the things you've learned in your earlier math classes, and I strongly encourage reviewing the Feynman lecture chapter as a kind of a written overview review that leads to this introduction of complex exponential in terms of the mathematical operations that you've learned, kind of the review of mathematical operations with more added mathematical maturity that comes from your training. Now, what I want you to do for this class, because if you are just doing something that you did in Physics 4A just all over again, like what's new here, this is a new semester. I want you to be able to introduce the additional complication, an addition to this model that makes it more realistic. And you have seen the LC circuit in your lab. So this suggests that it will oscillate forever, and it doesn't actually oscillate forever. The oscillation dies down because of the resistance that has to be somewhere in the system. So the more realistic system is really LRC circuit, and the way you do model it is with a resistor that's somewhere here. And when we start looking at it, this gets fairly complicated. And if we try to do it the exact same way we did for simple harmonic oscillator in Physics 4A, it gets much more difficult. So this is the motivation for me introducing what we introduced the last time, complex exponentials. So as a reminder, what you have covered in pre-calculus is this Euler's formula. E to the I theta is equal to cosine of theta plus I sine theta. And what I want to spend a little bit of time today is analyze this LRC circuit with this as our guess for what the charge on the capacitor should be. Our guess for the charge on the capacitor is going to be Q as a function of time will be some complex number times e to the, let me use b. I think b is least confusing among anything I can pick. E to the b times t. And what I want to emphasize here is that this is going to be a complex number. And this time, we are going to allow this to be a complex number. When we went through this first time, we didn't allow the exponential to be complex. That's why we went back and did the oscillatory solution. This time, we are going to allow this to be complex. Not imaginary or real, but a combination of imaginary and real part. Okay. So let me step back through the proper LRC circuit and just go through the Kirchhoff's rules again so that we have a proper equation of motion that we are going to solve for. So this is the LRC circuit. You have a capacitor, and let's say at time t equals 0, this capacitor is charged to some positive charge Q naught and negative charge Q naught. So that part is the same as before. And this capacitor is hooked up to an inductor, same as last time. And we will say that the way we have this set up, the amount of current that flows at time equals 0 is 0. So we close the switch at time equals 0, and the inductor forces current not to change it so suddenly. It has to change at a finite rate. And the new part that we are going to introduce now is the resistor. So this is what we want to analyze. The question we ask is the same question we ask for every other circuit. What is the current as a function of time? And what is the, you could, I guess whenever you have capacitor, you can ask it two different ways. You can ask it in terms of voltage, That's the one I actually prefer. But whenever you have capacitor, the voltage across capacitor is proportional to the charge. So voltage or charge. So the same two questions that we ask for any circuit is what is the current and what is the voltage difference across a particular element. And if you're talking about the capacitor, this will be related to the amount of charge on the capacitor. Okay, so we are going to use the same approach that we use for every single circuit since the DC circuit days. We are going to use Kirchhoff's rules. This is a simple circuit with no non-trivial junctions. So we are just going to use the loop rule. We define this loop starting from here, going around this way. Yep. So I'm going rushing through this because you have seen this at least half a dozen times, if not dozen times by now. So Kirchhoff's loop rule, which says that if I add up all the changes of voltage as I go around the loop, that adds up to 0. So say that this adds up to 0. So I start from here. I mark that point with the arrow so that I know where I'm starting. Starting from here, as I go across the capacitor, from negatively charged plate to the positively charged plate, I'll gain some voltage. And the amount of voltage I gain is Q over C, because I have these relationships memorized. The voltage change across a resistor is current times resistance. Voltage change across capacitor is the charge divided by capacitance. Voltage change across an inductor is inductance times di dt. So you should have it memorized, or if not, have it on your formula sheet. You should have it memorized and have it on your formula sheet, really. So that's the voltage rise as I go across the capacitor. As I go across the resistor, now I have a drop in voltage. So this is the term that we didn't have before I introduced the resistor there. So now I'm going to have it's going to be voltage drop, right? I'm saying this is the positive. Oh wait, I changed my label. Let me not confuse myself and flip this around so that the direction of the loop is the same direction as the direction of current. So as the positive current flows this way, the voltage across the resistor will be a voltage drop. So minus IR. And as I go across the inductor, should my voltage drop or rise? So I want you to think of the initial condition. At the very initially it's charged, and as current just begins to flow. So as I is starting from 0, rising to a very small value, as it rises to some small positive value, I get a voltage drop here. And here, should I get a voltage drop or rise? Drop, right? Because this didn't drop all of this voltage, so this has to drop the remainder of the voltage so that the loop adds up to 0. So here, this is what I'm going to write down. It's minus L di dt. And I just convince myself that to make it concrete, I'm thinking of the very initial condition, the time slightly after 0. My di dt is going to be positive because I'm imagining positive current beginning to flow and increasing in value. So this whole combination, minus L di dt, is a negative value as I expect it to be. Yeah? So all of this is equal to 0. So, all right. I stare at it a little bit for a little while, like I've done before, and realize that I have two unknowns, Q and current. They are both a function of time. So I have to rewrite this expression in terms of charge Q alone by using the relationship for amount of current through the capacitor. That's given by rate of change of the amount of charge on the capacitor. And so this is like third or fourth time we are doing this. I always go through this exercise trying to figure out which sign is it. Should it be plus or minus? So should it, in this particular case, should it be plus or minus? So this is how I want you to imagine it. Imagine at time equals 0. You start out with this much charge, and as you let time go from 0 to a time slightly after 0, the capacitor is discharging. So charge is decreasing. What's happening with the current? So I guess you have to know about two things. So I'm looking at this. So with the current, is the current going to be positive or negative? Positive, right? So that's the intuitive sense that you have from understanding what's going on in the circuit. And whichever sign I pick has to agree with that. If it doesn't agree, then it's wrong. So here, I'm not trying to come up with some complex set of rules. I'm just trying to pick a sign that gives me the correct answer. So my current should be positive, and my charge is decreasing. So is it plus or minus? I have to pick a minus sign here, so that with the decreasing charge, dq is negative, I get a positive current. So this is the exercise you need to go through, and you really do need to practice. This is not to sound like a broken record, but it's the exact same problem with half of we are having with Ampere's law. You listen to all of this, and you never think through it for yourself. So when you see it on the exam, you simply blank out and don't do well. This is an exercise you should be going through when you're working on homework, really. So, all right, so I have that. So that'll give me a way to rewrite my equation into this form. So plugging this I for both occurrences of I get Q over C minus or plus R dq dt. And plug this in here again, minus gets me plus again. Plus L, I already have a derivative, so it's going to be the second derivative. Second derivative of Q as a function of time is equal to 0. So this is my differential equation. And when you put this into standard form, the standard form is, what I call standard form is, where I solve this for the highest order derivative. But I guess it won't really help me at this stage. Let me do it anyway. I'll solve it for the highest order derivative. So the second time derivative of Q is equal to, so all of this moved over. So it'll be minus R divided by L, R over L, dq dt. And then the other term that I had last time also. Minus 1 over LC Q. Okay. So this is your second order ordinary differential equation. And if you're taking Math 3F, whatever differential equations class, they will tell you how to solve this differential equation. But for us, where we only require Math 3B, what we are going to do is we are going to guess an answer to this equation. So last time, this is what I said. In physics classes, even when you're at upper division, at graduate level, where you are supposed to know how to solve differential equations, what I claimed was that very often we don't actually do it the way mathematicians do. We have a convenient guess that happens to be a correct answer, and we simply check our guess. And let me tell you a little bit of secret. About 90% of those conveniently correct answers are exponentials. So I'm just going to guess an exponential. I'm going to guess my solution to this differential equation, Q as a function of time. I'm going to guess the answer here is going to be an exponential. So this is equal to Q naught times exponential of some coefficient times t, with a little bit of twist. The twist here, you might remember us doing this last time, and it didn't go well. But the twist here this time is that these two constant parameters that's here, we are going to allow them to be complex. They may be real, they may be imaginary, they might be a combination of real and imaginary. Complex in the sense of, it can be represented as A plus IB, where A and B are both real numbers. Okay? So let's plug it in and see. So when you plug it in, this is what you get. Double time derivative. Well, with exponential, those derivatives are super simple. Each derivative brings down a factor of b, right? So with the double time derivative, I get b squared times q naught all of this, or just q as a function of time, is equal to this coefficient here, minus r over L times the first, single derivative with respect to time. So I'll have a single factor of b, and the same function again. So q of t minus that 1 over LC times q of t. So you see that q of t simply cancels out from every single term, because that's one of the special property of exponential that you learned when you first took calculus, that when you take derivative, it doesn't change. And that property doesn't change just because it's now complex exponential. This b can be complex, and that property is still the same. So this simply cancels out from each one of these terms. And this is really why exponential is a convenient guess. It turns what used to be a calculus problem into an algebra problem. So the resulting expression here is b squared is equal to minus r over L b minus 1 over LC. It's an algebra expression with an unknown b. So anybody here know how to solve for b here? What do you know that can help you find the b here? Yeah, quadratic formula. It's an algebra problem. So that's really why we like to use exponential as our first guess. And for many problems, that'll be our final guess, the correct guess. And so here, this what used to be calculus problem boils down to an algebra problem of solving for a quadratic equation. So let me put this into an actual standard form for quadratic equations. So I should move this back. So it'll be b squared plus r over L, b plus 1 over LC is equal to 0. Well, that's the format for quadratic. I knew I shouldn't have used the b. So the way let me do a little switch of letters, and instead of a, b, and c that you normally use for quadratic formula, let me use alpha. So here what I'm going to refer to as alpha is this, 1. So alpha, this is beta, and this is the third letter in the Greek alphabet, gamma. So in terms of these new letters, the quadratic formula says that b there is equal to minus beta plus minus the square root of beta squared minus 4 alpha gamma over 2 alpha. Right? Okay, so just plug in these numbers that we have here, and let's see what we get. Beta is r over L. So this b is equal to r over L, or minus r over L, plus or minus square root of r over L squared, r over L squared, minus 4 times 1 times this, so minus 4 over LC, square rooted. The whole thing divided by 2 times 1, so divide by 2. Let me do a little bit of simplification. I'm going to do 2 simplifications. The first one will be easier. I'm just going to divide up 2 into this portion and this portion. So this first term will become minus r over 2L. And the next term, 2 will go into square root and get rid of this 4 there. The second simplification deserves a little bit of justification. And this is the part I want to justify. This here I'm going to rewrite it as square root of minus 4 over LC minus R squared over L squared. Yes, this is the same expression as this, but I should motivate why I'm doing this. It's a question of, I see two numbers are subtracting, right? And what this square root means has a qualitatively different meaning depending on which of these two quantities are bigger. And in a world where you can freely pick the value of resistance and value of whatever, then this can be anything. It can be 0, it can be -1, it can be negative, it can be positive. And in fact, if you read about damped simple harmonic oscillator in your textbook when you are studying for physics 4A, we didn't cover that in class because the asterisk section of your textbook. If you read it, then in fact the value of the sign here is the criterion for describing under-damped oscillator, critically damped oscillator, or over-damped oscillator. So the reason I want to write it this way is when you see oscillations like you saw in the lab, when you have an under-damped system, this quantity here is going to be positive. So I want to write it in a way that the quantity that we normally expect to be positive is set by itself. So there's a minus sign here pulled out so that so that it's clearer that most of the times this quantity, or for the conditions under which we are looking at it, this quantity here is negative. Yeah. So this is, I guess, how I would justify it. It's a matter of how we are picking the value of R. So, we studied this introduction with an actual LC circuit, the oscillatory circuit. So in the ideal case, what is the value of R? Like ideally you would say it's 0, right? 0 resistance, 0 of anything that's going to cause any energy dissipation. So as we start modeling this resistance R, we are going to start out with a small value of R. So that's where you look at it here. Look at this expression here. If R is 0, then this is 0, and this is some negative non-zero value. So as you increase the value of R, this whole thing is going to get less and less negative. At some value of R, it'll be 0. That's the value of R that critically damps this oscillator. And as you increase R further, you overdamp this oscillator. So that's the reason I'm writing it this way. So that when R is equal to 0, the quantity we have here is going to be positive. And it's clear that the whole thing that's inside the square root is negative. As you increase R, it'll eventually become 0. And then if you increase R further, this will be negative, meaning the whole thing under the square root will be positive. So we are not going to deal with the over-damped case. We are only going to deal with the under-damped case where there's still some amount of oscillation. So let me do that simplification here. So I already wrote down minus R over 2L. So it's going to be plus minus square root of minus 1 times this quantity here. With the 2 already factored in. So it's going to be 1 over LC minus R squared over 4L squared. Everyone okay with this expression? Okay, so let me do my last final step. I have a square root of minus 1. Well, that's the imaginary number I. So I'm going to say my B is equal to R or minus R over 2L plus or minus, and then I'm just going to factor this out by itself, plus or minus times I. And the remainder is going to be a positive number, so I can just keep it inside the square root. So square root of 1 over LC minus R squared over 4L squared. Good? So this is B is a complex number, as I have been telegraphing from the beginning. This B here, for the conditions under which we are looking at it, it's going to be a complex number. And before this Monday, we would have said that's a nonsense answer. We are going to do something different. What we are saying today is, well, that's not a nonsense answer. That is a meaningful answer. We are going to allow the exponent here to be complex. Okay? So let me write that out. So with the complex exponent here, this is what our guess ends up being. So I guess black is the best color. So with the complex b, this that I'm going to plug in and then factor things out to simplify it a little bit, it's going to look like this. So charge as a function of time is equal to some initial charge Q naught times exponential of all of this. So I'm going to write in the first term first. And you guys all remember the exponential algebra, right? When things add in the exponent, then when you separate it, it's going to be the product of e to the this times e to the this, right? So I'm going to have e to the minus r over 2l times t, that's this time t here. So this is one time dependence that's going to be in our solution. And one additional time dependence will come from the second term. It'll be, so times exponential of plus or minus. And then I'm just going to copy this in. I times, actually let me do one simplification. I'm going to define a quantity that I'm going to call omega. So this quantity here, I'm going to define this entire square root thing as omega, or the natural oscillation frequency. And so it's a plus minus I omega t. Okay? And we are going to say this is actually a meaningful answer. And I hope you can see some parts of it that remind you of what you saw in the lab. Like, so in the lab, did you see anything that looked exponential? Think back to your LC circuit that you did in the lab. So in case, it's maybe easier to see the picture of what you saw. So in the lab, this is what you should have seen. That, the applied voltage suddenly changes and your circuit rings. Like this is what you have seen, right, in the lab? So if you're having trouble seeing the exponential portion of this, let me draw the envelope. So, I mean, you can clearly see the oscillatory portion, right? That's the thing you're supposed to measure frequency of or period of. The envelope is this. When we say envelope, what we mean is we imagine this entire form as a result of a product. As a product of an oscillatory function that's the actual just the sine wave, or in this case cosine, whose amplitude is not changing. And you imagine factoring out this variation of amplitude to a single non-oscillatory function that you are going to multiply to this oscillatory function. That's what we mean by envelope. It's because that's sort of what it looks like. This is the envelope of this function. So each time where it's a maximum here, local maximum here, that's the point that's showing the envelope. And so the envelope sort of gets mirrored. So here's the envelope on the other side. And so what does this envelope look like? Yeah, this is the exponential decay, right? And that's what you are saying here. This is the exponential decay function that is being multiplied to your oscillatory function. Because when you have this is a complex or imaginary exponential, then whenever you see something like e to the I omega t, you recall this formula here. So e to the I omega t can be expanded out this way. Cosine of omega t plus I times the sine of omega t. Okay, let me pause and address one last question. So as you look at this, I hope if you think about this for too long or the right amount of time. I hope it at some point bothers you that this charge as a function of time, that this is a complex number. Because, I mean, even the word imaginary number has this slur attached to it. It's an imaginary number. The way it was introduced to you was that, you can count 1, 2, 3 apples, but you cannot count an eye apple. Like, what does 2-eye apple mean? So at least when it was originally introduced, there's this stigma attached to the imaginary number I, that it does not represent anything physical. You are trying to get an answer for a physical quantity, for a physical amount of charge T. So, but the solution that you guessed and got an answer to is a complex function. So how do you go from something that's complex, that has imaginary stuff attached to it, to something that's supposed to be measurable and real? Yes?
Square.
So you can square if you are, that's what we do in quantum mechanics actually. You don't quite square, you multiply with a complex conjugate. That's how you take the absolute value square over any complex number. We're not going to go to that today. So that's one mathematical procedure. Usually you do that when you are trying to get at something that's kind of like an energy. So in quantum mechanics, what you do is you have something called the probability amplitude that has no physical meaning. But by squaring it, you get the probability density that has an actual physical meaning. You might have heard these words in chemistry, maybe. So that's physics 4C. We won't get there. Here, we are trying to get to not the amount of energy that's stored in the charge, but the actual, so this is what we would like. We want to know the actual amount of charge on the capacitor as a real function. That's really what we are trying to get. And it feels like we are somewhere close here because we have something that's oscillatory multiplying with something that's exponential, which matches what we saw experimentally. So there should be a single mathematical step where we can get from something that's complex and maybe doesn't quite exactly represent the physical picture to something that is real, and we can say without any doubt that that represents a physical picture. So, any ideas? Well, once I say it, it's going to sound silly. So the way we get to this real function of Q of t is that we are just going to say, we are going to put this through the mathematical operation of taking the real part. So we are going to say our real Q of t is going to be equal to this complex Q of t that we found, except we are only going to take the real part of this complex Q of t. This is the last step that will get you from this complex function to a real function, which you can say, like, you don't need to interpret anything. You can say, well, that is my Q of t as a function of time. So here, let me do it once naively, and then I will show you an additional consideration that you should remember for a more complicated question. Let me show you a naive, very reasonable mistake you can make, and I will show you how to correct that mistake. So when you imagine taking the real value here, so you might take this and write down, all right, so my Q of t as a complex function is equal to, I have this real part, let's factor that out, Q naught e to the minus r over 2lt times, and I have this portion which is complex. I'm going to use Euler's formula to separate out the real part and imaginary part, and say that this is equal to cosine of omega t plus or minus I times the sine of omega t. Yep. And what I would naively say is that when I take the real part of this to get the actual, to get the actual charge as a function of time. So taking real part, that's exactly what it sounds like. I look at this imaginary portion, say I don't want it, so don't write it down. I simply copy down the real parts. The Q naught times e to the minus Q naught times e to the minus r over 2lt times the real part, cosine of omega t. And I keep saying this is what you would do naively, because you would do it, and this will actually be the correct answer. So you try to put this into the initial condition, right? Initial condition where you say, you know, at time equals 0, you have some amount of charge, and at time equals 0, you have 0 current. And if you use this function as your guess the solution, use this real function as your guess the solution to it, it will satisfy all the conditions. You plug this into this differential equation, you should see that it all works out, I think. Well, it works out in at least one sense. It works out to give you the correct initial charge. But I think the place where you will begin to see it fail is if you try to look at the current. So let me give you let me tweak this problem a little bit and show you where this does not actually, in no way, is the correct answer, and show you how you should have interpreted all of this so that you can get the correct answer every single time. So this is the scenario I want you to think about. So for this particular setup, I started out with this set of initial conditions. At time equals 0, my current is 0. And at time equals 0, my charge is Q naught. That's how I started out this setup, right? And what I want you to imagine is, imagine shifting the time a little bit so that this is your time equals 0. So at your time equals 0, initial condition is not that all the energy is in the capacitor and no energy in the inductor, but all the energy is in the inductor and no energy in the capacitor. Now, when you try to come up with a solution that matches this, this new initial condition, where you say, let me do the new initial condition in red, where you say current at time equals 0 is your maximum current. So all the energy is in the inductor. And the charge at time equals 0 is 0. No energy on the capacitor. Then the things we did seems to break down, because so here we are working with a general solution. So nothing here really should have changed. And all you are supposed to do is, you know, plug in the initial conditions here and determine these constant parameters. But so if you start from this expression here, no value of Q naught will give you the correct answer, because when time equals 0, well, so Q naught is Q naught 0? You don't want to say Q naught is equal to 0. That sounds like the trivial solution. So where did I go wrong? Where was the naive mistake made? So I will tell you this much. Like up to this point, so I can at least get back this far and do the correct things. All the mistakes that were made was made on this corner of the board. Well, there's really one mistake that was made. So I really did mean when I said that this parameter here is complex. This is really a complex number. And I guess this is really the significance of saying that a number is a complex number. When you have a real number has only one free parameter. Complex number always has two free parameters. It has A and B. In fact, do you guys remember complex plane? Wait, complex plane gets covered in pre-calculus, right? Geometric representation with the x-axis being real, y-axis being imaginary. This is pre-calculus material, I'm pretty sure. Yeah. review it when you need to. So the reason I want to bring a complex plane is your textbook will talk about these circuits in terms of phasor. And phasor is very complicated, I don't know, it never really made sense to me. But if you treat this as complex numbers, and you think of the phasor diagrams in your textbook as a simply graphical representation of complex plane, then everything is consistent, makes mathematical sense. So what I'm trying to say, this Q naught here, this constant parameter, you actually need two free parameters to describe it. The way most of you were imagining was this Q naught was simply a real number, Q naught here. Well, actually, if you are thinking of something that has magnitude Q naught, there's an infinite number of possible values that this can take. Infinite number of these, any of the points around this circle of radius Q naught. So this constant value, it could have taken this value, I Q naught, where Q naught is still real. Or it could have taken any other intermediate value, any other point where, so it would be the Q naught real and Q naught imaginary. The only condition you would have to satisfy is that the length of this is, so the real squared plus imaginary squared is equal to Q naught squared. So, so there's a second way of representing complex numbers that makes this geometric relationship clearer. So this is the Cartesian representation. The other way of representing complex number is so complex number G as some magnitude, I don't want to use R. Well, magnitude G, the absolute, some kind of idea of length of G times e to the I theta. And when you write out e to the I theta, that's cosine theta plus I sine theta. The cosine theta portion gives you the projection along the real or the x-axis. And so sine theta portion gives you the projection along the y or the imaginary axis. So that was the mistake being made. So when I was taking the real part here, I couldn't just take the real part of this portion of the expression alone. Really what I had to consider was this, that Q naught was a complex number, that this is really represented as A plus IB, and this is represented as C plus ID. And before I take the real part, I have to imagine expanding this out. And when you have A plus IB times C plus ID, the real part of this entire product is not simply A times C. Because let me write this out. When you write out this is what you get. A times C, so that is there. It's part of it. But when you do the whole cross product, cross multiply or whatever, when you expand it out, you have, so IB times ID, that will give you I squared or minus 1 times B times D. So you have AC minus BD. So this is the entirety of the real part. And then you have plus IB times C plus ID times A. So I times BC plus AD. So the mistake that's being made here is that I'm taking only this portion and think that's the entire real part, where there's this minus BD also. So, if you're interested, that's where you can sort of rewrite this in terms of, so that's where you get actually your two free parameters that you need for this second order differential equation. So to go from this general solution to particular solution, you needed to determine two free parameters. And this contains actually both of those two free parameters in terms of its real part and the imaginary part. This is the place where it's most clear, the advantage of using this complex exponential to look for a solution to this differential equation is. The advantage is clearest in this example, because if you're imagining guessing this solution using any other real function, it's going to be much, much harder. With this complex exponential, there's a complication that comes into the interpretation, but you can at least follow the algebra that you have seen. The algebra is nothing that you couldn't handle. It's the final interpretation piece that muddies the water a little bit.